So let's start the class. Hello. Yes. Audible. So hello everyone. Uh, in this particular week, we are with this. This is 10th week of the course transport phenomena of non-Newtonian fluid, and in this week, particularly, there was 4 lectures, and in that we started with the building up the basics of this mass transfer. So far we have had this transfer of momentum and transfer of heat in the problems that we have solved related to the transport phenomena, and again with the Newtonian and non-Newtonian fluids. But in this particular week, we basically started building up the foundation for this upcoming weeks, that will be involving the another component of the transport phenomena, which is the transport of species, which is the mass transfer part of the the transport phenomena. That So the first lecture of this particular 10th week was the basics of the mass transfer, the diffusion, the diffusion of component A in a non-diffusing component B, or like counter diffusion of each other. So what we have seen, that we have built the basics of basic definition of what are the different methods in which the mass flux can be expressed, and what are the different quantities or different variables can be used for this species, or the driving force for the mass transfer. So that we have seen. So that was the first lecture of the week, and second lecture we had solved some questions around that. And in the third lecture, what we were doing is around the spherical particle, how the mass transfer is happening with the momentum transfer, and if the thermal effects are also there with the diffusivity, then how the entire transport phenomena will be modeled. For example, here there if the surface of the sphere is the catalyst, then on the surface of the catalyst there will be reaction also. So how this reactive species production or consumption will be related to the temperature, and at the same time with the fluid flow part, right? So far in this particular week, we have not discussed much with this part of inertia, when the inertia of the fluid motion is also considered, because the calculations become cumbersome, and it becomes difficult for us to keep those kind of problem in the course kind of curriculum. Rather, those kind of problems can be attempted with the basics intact that we are going to learn, and these all basics will be helping you to build up the problems of those kind where the inertial influence and everything you are including, and using different numerical schemes to solve them, right? So let me just present my screen, and then I will be going to that. So screen one I am presenting. Okay. So, and this one is this, right? So this is week 10 of the course Transport Phenomena of Non-Newtonian Fluids, and myself Saurabh Dubey, and a research scholar at IIT Guwahati Center for Nanotechnology. And so far we have seen that these were the basic definitions of basic types of different non-Newtonian fluids that are under consideration, right? So let me just present the lectures so that things become easy. So we are in the week 10, so I will be just opening the week 10 lecture. Yes, so these were the lectures that we have probably gone with. So what I'm saying is the lecture 31 was around this basics of mass transfer. So let me just write it. So first B 10, right? Here first lecture was on basics of mass transfer. Okay, basics of mass transfer, basics of diffusion, and diffusion through stagnant okay stagnant gas film, right? And second is what? Second lecture of the week we had dealt with this mass transfer combined with chemical reaction. Okay, mass transfer combined with chemical reaction. Reactions, right? And then this non-isothermal diffusive mass transfer and forced convection mass transfer. When we had this non-isothermal diffusive mass transfer and forced convective mass transfer, right? And the next, the last lecture of the week was on this simultaneous heat and mass transfer, right? So I think this was the last one. This was the last one. Just fix it here, right? So this is the last one. So this is the fourth one, right? This is the second. Okay. What I am saying is this was the seven. So this was 30, 31, 32. This is 31, 32, 33, 33 in this one, and 34. Fourth, right? What is this? This is the 33rd lecture. 34th lecture was simultaneous heat and mass transfer, right? So let's see questions on them. So what I'm saying is I will be solving the questions and connecting the course with this. So this particular lecture will be helping you. Let me just see if things are okay. Okay, so yes. So this is diffusivity, right? Let's save it. Yes. So this should be square. This should be square, right? So consider a binary gas system of A and B at constant temperature and pressure of 300 Kelvin. right? So you are having this binary gas, A and B, constant temperature and pressure. So P is what? Temperature is what? 300 Kelvin, and pressure is what? 1 atmosphere, respectively. In a pipe of length is what? 25 centimeter, right? Diffusivity of this system is, so you are having DAB. The DAB value is what? DAB value, let me write it here, 7.86 into 10 power minus 4 into square percent, right? So this diffusivity value you are having, just make it power. Okay. Okay. At one end of the pipe, the partial pressure of A is this. So you are given with PA. So suppose this is the pipe. Suppose this is that pipe, right? And in this pipe, if suppose PA is here and PB is PA 1 and PA is given as 0.6018, right? So PA equals to 0.6018, and at the another end it is PA naught is given at one end, and another end PA 1 is given here. PA 2 is what? Other end 0.2018, right? So what I am saying is, if what is the molar flux of A at steady state condition in kilomole per meter cube per second is what? Okay, so just attempt this. Okay, please attempt this and then we will be discussing it. So what is the molar flux of A at steady state condition? That is the question that is asked to you. And these all are what? So I will be anyway rectifying. I just read it. That's why it is having someone. It will be corrected while we are solving, right? So what is the mass flux? So in order to solve this, uh, we will be employing very basic laws. So if you see that, let me just change the color. Here the temperature is what? 300 Kelvin, right? And this pressure is what? Pressure means total pressure is what? And you are given that there is a pipe. Suppose this is that pipe, right? In that pipe, here and here, you are given the pressure. But the Z2 minus, suppose it is Z2, it is Z1, this is, let me just write Z1, Z2. So Z2 minus Z1 is given 25 into 10 to the minus 2. What you got? Let me just see. Okay. Okay, so yes. So what Z2 minus Z1 is this one? If you see, length is 25 centimeters. So it is 10 to the minus 2 meter, right? Now BAB is what? You know, 7.86 into 10 to the minus 4 meters per second. PA1 equals to 0.6. So CA1 partial pressure given, so concentration will be given by R2, and constant pressure is given. And similarly, PA2 equals to 0.2. CA2 equals to PA2 divided by R2. right? Now if you do this, okay, so you know that this JA flux equals to us minus DAB fixed line dCA by dZ. Okay, so when you use this equation, you use this equation and solve. Take dz that side, so it will give you JA dz. Integrate it from Z1 to Z2. DAB. Let me just see why it is plus 1. So now it is charging. DAB CA1 to CA2 DCA. Okay. Solving this, you will get JA equals to minus PA2 minus PA1. Okay. RT Z2 minus Z1. Okay. So this will give you all the values are known right now, right? 7.86 into 10 to the power minus 4, 0.6 minus 0.2 into 1.0135 into 10 to the power 5 Pascal and whole divided by what? 8314 into 300 into 0.2, right? So solving this, what you will get? JA equals to what? 5.11 into 10 to the power minus 5 kilo mole per meter square answer, right? So this is which option in the here? It is C option. C is correct. Okay. So this question we have solved. Question 1 is done. Let's go for question 2. So this was very basic formula that comes that was the part of the first lecture of the week. The basics of mass transfer and diffusion through stagnant gas stream. Okay, so we will be revisiting once in a while wherever we will get time. We are going to solve around more than 10 question or 10 question, and then meanwhile we will be revising the slides that were the content of the week, right? So, but basically first we will be focusing on this questions, right? Because sometimes at the end we are having very less time to solve those questions, and we have to rush around. This time what I observed is what I done is I have done that I will be starting this questions from the beginning only, and then meanwhile I will be going through this theory solutions and then coming back to the question. So through the question we will be learning. Okay, so now you see that here at this junction you had the partial pressure of 0.4, right? Here you had this partial pressure of 0.4, right? And you converted it to CA by RT, right? CA, and it is CA, it is CA1, right? CA1. Okay. So you see that wherever the partial pressure is more, the presence of the component A of the gas is more, and that's why the contribution of the pressure, partial pressure, because of A is more in the total pressure, which is 1 atmosphere at any of the, right? So that is the main thing. And next question is, let me just see. Yes. So this is the next question that we are going to solve, right? Uh, Let me just fix it. It is square. It should also be square. Now things are okay. So let me just, if you want, I can expand, but it is okay. The size is okay. I don't think it has to be. This much is okay. So consider a liquid A filled in a column of height 13 centimeter, right? Where the distance from the liquid level to the top of the column is 11.14 centimeter, right? Component A is evaporating. Let me just fix it. So component A is evaporating into stagnant air B at a total pressure of 717 mm of Hg, right? Let me just add water. So what I'm saying is this mm of Hg, right? This unit we have to change, and everything we will be solving in the same unit, or if to keep the same unit, we have to be considering the units of other variable in this in that manner also. Okay. So consider a liquid A filled in a column of height 13 centimeter, where the distance from the liquid level to top of the column is 11.4. Okay. So let's draw this picture. Yes. So what I'm saying is, suppose this is that column. The total height is what? 40 centimeter. Right? And here the liquid column is there. Okay. And this liquid which is here, this liquid is having height what? 11.14. Right? Component A is evaporating into a stagnant B. Suppose here air is B and this is A. This is evaporating, right? Stagnant B. At a stagnant B means and B equals to 0. Stagnant B at a total pressure of P total is what? 770 mm of Hg. And temperature is what? 25 degrees Celsius. The diffusivity of the system is, so DAB, AB is the component, so DAB is what? 0.088 centimeters square. Vapor pressure of A is DAV is what? Vapor pressure of A is what? 23.81 mMs. Density of A is what? Okay. 1.65 gram per cc. And surface area of the liquid exposed for evaporation is this area. 2.29 centimeters. what is the rate of evaporation in gram per hour? Okay, W A is asked, gram per hour. Keep unit. Molecular weight of A is MA. MWA is what? 164.4 gram per gram mole. Useful equation to solve the problem is, so equation to solve the problem is given. So even it is not given, then also you can solve. But here it is given. So one sort of simplicity is there, right? Let me just keep it here. Yes. Okay, so this is given here. So how you are going to solve it? So through the problems we are understanding the entire thing, right? And then we will see that very quickly we will go through the slides and main equations we will be revising. But I will be mostly keeping you with the questions only because in the classes lots of theory you have uh, gone with, and this is a kind of practice. If you are practicing problems, then if you are connecting those problems to the theory which is being taught in the class, then you will be anyway revising the whole syllabus. So now suppose this is the equation. So here if you see flux at any z location, so at z equals to z1, which is the surface from where the evaporation is happening, which is 11.14 centimeter height in that 13 centimeter of the column. Okay, concentration is what? Uh, Here they are saying that concentration is what? 70. Okay, that's what I am thinking. So in the ATM we have to convert, right? So it is 760 mm of HG, right? So that if you convert, so you know 1 ATM equals to 760, and in this one you have 770, right? Once you convert that, what you are going to get, the value of C. So C you are not using, we are using this expression. So it is P. P is what? In atmosphere 770 divided by 760 atmosphere. Then this is in centimeter here only it is used. Okay, then divided by what? RT 22.6 into 11.1%, right? And now just take this. Okay. So here ln EA2 PB2 divided by PB1, right? So PB2 is what? That is the question. So you came to know that at that interface, right? So PB1 at the interface, if you see, A is how much? 23.81 is the vapor pressure, right? I think 23.81 is the vapor pressure. Yes, yes. So, and it is asked at a steady state. So, anyway, yeah, no steady state. So, here 770 minus 23.8. So, and at another end there will be no V2 because there V is 0. So if you write it in terms of V2 only, then whatever pressure is there, it is the pressure, right? So it is PT minus PA1, or here if you write PT minus PA1, it is PT minus PA1 is 0, right? Once you solve it, what you are going to get is 1.03 into 10 to the power minus 8 gram mole per centimeter square second, right? Now, in this problem, what is asked? If you see, they are asking, this is flux. They are asking what? They are asking evaporation, rate of evaporation in gram per hour, right? So to convert it to rate of evaporation, what you are going to do? Area, and then it is asked in gram. It is in mole. So you have to convert that. So rate in mass unit equals to molecular weight into surface area. So it is 1.03 into 10 to the minus 8 gram mole per centimeters per second multiplied by 164.4 gram per gram mole multiplied by 2.29 centimeters square multiplied by, this is for unit. To convert that thing into hours so that you will have answers in gram per hour. Okay, so that is done. This question is also done. So it is 0.0139. Which option? 0.0139. Let's look at the answer. Let's save it. So what I am saying is, let me just see if things are okay. Yes. So what I am saying is, the next question, let's solve. Okay. So the next question says, let me just explain it here. Consider absorption of component A of molecular weight 71 gram per gram mole into a falling film of length 13 centimeters. So you see all the problems that we are dealing here is the same problem or almost similar case study we had in the class, right? So in the weekly lecture you have had similar case studies, but there everything was happening with the expressions, right? It was the derivation kind of thing. But here you are having some numerical problem. So with the numbers, if you are solving the same problem, then it becomes easy for you to appreciate what is happening, which component is going which place, what is the entire system. You can feel it, right? Uh, it becomes as if it is a real problem. So consider absorption of component A of molecular weight 71 gram per gram mole into a falling liquid film of length 13 centimeter and width 8.8 centimeter, right? The maximum velocity of the liquid film is 26.55 centimeter per second, right? And diffusivity of A into liquid film of B is 1.26 into 10 to the power minus 5 centimeter square per second, right? The density of A is 0.998 gram per cc and saturation concentration of A in B is 0.826 gram of A per 100 gram of B, right? So you see that it is like very less concentration of A is dissolving into B, right? What is the rate of absorption of A into liquid film in gram mole per hour? Useful equation to solve the problems. So you see that everywhere you are given with the useful equation. So only if you are knowing the concepts, then it is you can solve the problem. Okay, you don't need to memorize all the steps. Just the concepts are needed. So let me just solve it for you. And we are having around 10. So you can pause it. These videos will be recorded. You can pause it and then you can actually go through solve it and then see the solution whatever I am solving. It will help you to get one trial from your side, right? So you are actually giving one trial to them, and that is important. So let's take the expression that is given. So we are going to solve this problem, right? So it is given, and you are having this falling thing, right? So if you see, consider the absorption of a gas A of component this into a falling film then A, and with this, right? So let me just take the graph. This will help you. Okay. So yes, this is that graph. So I will be just taking this looking thing. Okay, so this is that entire picture under which you are going to solve it, right? So this, so we will be having the discussion of the same while solving this. Okay. So so we have seen. So let me just discuss this slide and then we will solve this question. So this will be a kind of revision session, and at the same time you will have overall understanding of the problem. So just actually helps. Okay, so so diffusion into a falling liquid film. So diffusion is happening in a falling liquid film. For example of force convection mass transfer. Okay, so here if you see, so viscous flow and diffusion are under such conditions that velocity field can be considered as unaffected by diffusion, right? Velocity field is unaffected by diffusion, it is assumed, right? Consider that the absorption of gas A, okay, in laminar falling film of liquid B, it is happening, right? So B is falling. So material A is only slightly soluble in B. So for example, in this one, you have seen that the kind of concentration that you are given, it shows that this is A is slightly soluble in B, and here component A is getting absorbed, which is having this molecular weight in the falling liquid film of B. Okay, so B component is what? Is then 30 centimeter and width of this. The maximum velocity of the liquid film is this. So here maximum velocity are given. So if you see that diffusion takes place, A is slightly reduced so that the viscosity of the liquid B is unaffected, and then diffusion takes place so slowly in the liquid film that A will not penetrate very far into the film, right? So it is not penetrating very far into the film, though the penetration distance is small in comparison with the film thickness. So that's what. So in this diagram, this is the falling film of B, and A is here, and it is diffusing into B. So you see that wherever A is here at the interface, we are having concentration to be maximum here, and then it decreases. So this concentration is decreasing with respect to what? With respect to X also and with respect to Z also, because this is falling like this. Okay, and same will happen with the temperature if temperature is there, right? So if you see that this is width, this is L, and here the element of delta X, delta Z has been taken. Now to solve, and the velocity profile is assumed that it is not depending on the diffusion, so thick and line. Viscosity, flow, viscous flow and the diffusion are under such condition that velocity field can be considered unaffected by diffusion. So diffusion is happening in X, right? Uh, so velocity field is considered to be like this. Okay. So in such problem, so again you start with the equation of continuity. So accordingly, it is satisfied equation of continuity using that you are not having any progression. So this Z is not there. Okay. So Vz is here. Okay, Vz is here. Del Vz by del Z. Okay, it is not changing with Z because Vz is only function of X, and Vx is not a Vy factor. So it will be satisfied using equation of motion in X direction. We will have that del P by del X is not equal to 0, means E is not the function of X, and similarly equation of motion in Y direction component will give P is not function of Y, right? So now Z component of equation of motion to solve, you will see this. Okay, from here everything will be going to 0. Just this term will be remaining, right? E is then minus LP by Z plus mu. This one, Vz rho Vz, right? And it is falling through. It is there, right? And this is also there. And these two term, pressure and this term, you have considered there to be in this, right? So that's what I wanted to say. Now, if you see solid, this is the expression for Vz that you got. Ug by mu this one, and when Vz you calculate, go for the transfer measurement at x equals to 0, Vz is maximum. You understand? At x equals to 0, Vz will be maximum. This is to be high. At x equals to delta, Vz equals to 0. So delta is any thickness inside here. Okay, x equals to delta. Okay, Vz is what? Delta Vz equals to 0. Delta is the thickness. Or this here. So from there C2 you got, and you got this expression for Vz, right? Now you are having Vz, right? This is your beautiful expression for Vz. This shows that the gravity is, is having effect. Thickness of film is having effect, and then position from the interface is also having effect. Viscosity will be inversely proportional to the Vz, right? So from here vz max you got. So in this problem, if you see that you are given with this vz value, vz max you are given with the maximum velocity of the liquid film is this. So this vz max you are given with this expression. So you are given with vz max, you are given with dab, you are given with l, you are given with w, okay, and you are given with cnr. If you have to see that concentration saturation, so you are given with everything. So you can solve it anyway. But we will be looking at derivation, and then we will be coming to the content of the question, right? So let's complete it. So once you had this for the species transfer equation is this one. See, this is for reaction, this is for diffusion, and this is for convective concentration mass transfer. Concentration transfer, right? So it is steady state, and these terms we are not considering because of the inertia. But in this one, we have to consider Vz because Vz is there, and then Ca by del Z is considered. So you see that inertial terms you are actually having here, and you just put it Ca and this. And the third equation, when you solve under the condition that Z equals to 0, Ca equals to 0, okay, then I'm assuming that then here, Z equals to 0 is here. So concentration, no concentration came into this, right? Z equals to x equals to 0. So here you see here x square is so two independent variables are there. So you have to be very cautious. So it indicates that the field consists of pure B at the top, right? And it indicates that the liquid gas interface concentration of A is determined by solubility of A and B, which is Cm. That can be calculated based on the value which is given. And at x equals to delta, then Ca by del x equals to 0, and this x equals to delta is the plate. So now, very important after this, just calculations are there. So now one can get only a limiting expression for Ca valid for short contact time, i.e. for a small value of L by Vz max. Vz max L. Okay. According to the problem, substance A has penetrated only a short distance into the cylinder. So A has impression that film is moving throughout with constant velocity equal to Vz max. A does not penetrate very far, i.e. it does not sense presence of solid water. Therefore, if the film were infinite thickness moving with the velocity Vz max, then the diffusion material would not sense the difference in the velocity. Okay. So it is an assumption, and then this physical argument suggests that one can get very approximate result if the equation 3, which is this one, okay, 3, and its boundary conditions are approximated as below. This is this, so here, so no change in velocity. Okay, so delta is very small, so x is very small in this distance. Okay, so this you have in this. So at x equals to infinite, C is 0. Okay, so can be solved using the combined 7 along with the boundary 8 to 10 can be by using method of combination of variables. Combination of variables we have started using. So this is the combination of variables. Ca equals to Ca by Ca0, Ca by Ca, and this is eta, and this is x, we have given this. And this is combination of variable. X and Z is here, right? So if you see this combination of variable, then what you are going to get is, once you solve it, the expression becomes this one. Just resubstitute it. Now convert the derivative of equation 7a into the derivative with respect to combined variable. Once you solve it, what you are going to get is in terms of combined variable, both sides you are going to get each other. And now it is a kind of ordinary equation that you can solve, right? Under the given assumptions, that is energy being converted. So this is this kind of equation, and you solve this very easily, rearranging it and solving you will get okay, finally the expression that is given to you, right? This expression. So this is finally the flux, okay, no local mass. Okay. So this is the one that you will get, see, concentration variation, okay. And then when you consider no local mass flux at the gas liquid interface, then in that case some rearrangement will happen and you will get this. And when total molar flow rate of A across being absorbed by and then that is this one. So if you see that, you are able to get the expression that is given. So this is this particular lecture was all about. So let us solve the problem first, and then we will be actually looking at the main things that are given over here, right? So the problem says let me just note this. Okay, so the problem says consider absorption of component A, molecular weight is 71 gram per gram mole, E into a falling liquid film of length 13 centimeter and width 8.8 centimeter. The maximum velocity of the liquid film is 26.55 centimeter per second, and the visibility of A into the liquid film B is 1.26 into 10 minus 12 centimeters square per second. The density of A is 0.998 gram per centimeter, and saturation concentration of A in B is 0.823 gram of A per 100 gram of B. What is the rate of absorption of A into liquid film in gram mole per hour? Useful equation is given like this, right? This was the schematic that is here. Okay, now if you see this, so our PPT is here. Let me just take the PPT set. Yes. Okay, so let's solve it. We are in the third question. So you are given with this VZ max equals to what? 26.55 centimeter per second, right? And DAB is what? 1.26 into 10 to the power minus 5 centimeter square per second. L equals to what? 13 centimeter. W equals to what? 8.8 centimeter. These are the W and B. So L is what? 13 centimeter. W is what? 8.8 centimeter. DAB you know, right? Now MA, molecular weight you are given with. So CA naught if you want to calculate, you are given that rho W is in the mole, gram mole per meter centimeter cube like that. 9.8 into 0.08 divided by 70 will give you 1.16 into 10 to the minus 4 gram mole per centimeter, right? And then WA equals to rate of absorption. Okay, it will give you given value W Okay, LCA naught under root of 4 VAB VZ max divided by IL, right? So what I'm saying is, let's take this. It is 8.8 into 13 into gram mole per cent. So you see that just all the steps I have wrote for you. Just follow this step by step. You will be getting the answer to the given question. So this was the problem related to the problem that is the part of your question. The lecture second of this particular, right? So what is the answer? 0.27. Okay, it is correct answer, right? So it is done now. Let's consider the next question. So here if you see that, let me just make it a bit bigger. A, B, and this is C, this is D. Okay, so option A is this one, B is this one, C is this one, and D is this one. So you may have this is also in this UG mass transfer courses. So you may have gone through this, but let me just redive it for you, or I can re-redive it for you, because re-deriving it will help you, right? So consider a gas liquid system in spherical geometry by considering droplet of liquid A of radius R1. Okay, droplet of liquid A of radius R1 is being suspended in a stream of gas B, right? There exists a spherical stagnant gas film of component B of the radius R2, right? Surrounding the liquid droplet. The concentration of A in gas phase at these two locations are given by this law. Okay. Na XA1 and XA2. What is the flux of A at the droplet surface? At R equals to R1, right? So this is the question. So let's first save it and then solve it. So this question, if you see this, this is very similar to what the standard problem that the basic definition of fixed y is about, right? The basic definition of fixed y is also same. Just here the spherical, that's just the geometry is different. So here you are having this spherical geometry, right? So if you see this, then it is fourth question. Okay. So gas liquid system is there, then spherical geometry is there. So A is that droplet which is having R1 radius, and B is the stream of gas. Okay, so because of that there is a stagnant gas film of that B of radius R2 surrounding the liquid film droplet, right? So the concentration of A in gas phase at these two locations are X7 and X2. What is this flux of A at the droplet surface, right? If you solve this, let me just read it. So the color I will be changing to something else. Okay, so let's use that. Okay, so solution is okay. So molar balance on A over a spherical cell of thickness dr, right? So what I'm saying doing is 4 pi r square is the area of the, suppose through this area Na is the flux, it is at r location minus 4 pi r plus dr, okay, square into Na r plus dr. So what is this? This is that spherical. Suppose this is R1, and here suppose that is the gas B fit, suppose it is R2. In between here, if you consider a thickness dr thickness of this cell. So at a first location R, and then it is R plus dr, right? And this is what R plus dr. This is R, right? So so here boundary condition is what? So simplify and divide by 4 pi dr and limit dr equals to 0. Simplify and divide. This is a very equation by 4 pi dr and take limit dr tends to 0. Right? Limit dr tends to 0. If you take, then you are going to get d by dr of r square m equals to 0. Guys, r square m equals to constant C1. Now, boundary condition is what? Na equals to Na at r equals to r1. That is r square Na equals to r1 square Na. Okay. Now, but Na equals to minus C dAB dxa by dr plus xa Na plus Nb. So solving this, Na equals to minus C dAB. This will become 0. Okay. So this is 0 because B is not, okay, and minus X. So you just rearrange and solve it. Na into r square is what? So it is Na at r equals to r. This was c square equals to what? Minus c dab 1 minus xc r square dxa by dr. And this Na at r बराबर r1 into r1 square, it will give you minus c dab by 1 minus x r square dx by dr. Right? Okay. So this at r1 square Na r बराबर r1 dr by r square. This will give you minus c dab by 1 minus x dx. And then this r1 square Na r बराबर r1, it will give you 1 by r2 by r1 equals to minus c dab. This is what? Minus ln minus 1 minus xa 1 to xa. Right? Solving this, what you will get? r1 square Na r बराबर r1 1 by r1 minus 1 by r2 equals to c dab ln 1 minus xa2 divided by 1 minus xa. Okay, so this will give you what? Na at r equals to r1 equals to c dab divided by r2 minus r1 r2 by r1 ln x b2, which is 1 minus xa2, divided by x b1, which is 1 minus xa, right? This is answer. So this is what? r2 r1 r2 by r1 b2 b1 r2 r1 r2 by r1 b2 b1. This is the option. r2 r1 r2 by r1 r2 r1. This is answer. B is correct answer, right? So now it is done, right? So let us save it and move to the next. So today I am giving you revision of all the things. So very basic mass transfer. You may again go through. So everything was the part of discussion in the initial lecture of this particular week, which is the week 10, right? So let's see question number 5. So this is very good question as per this concept is there, right? So let me just fix it like this. So these units I am fixing because okay, this is anyway understood, but anyway I will read. Okay, so consider a case of hot vapor A diffusing at a steady state through the stagnant film of non-condensable gas B on the cold surface at y equals to 0. So this is another case where this temperature also came into the picture, right? But let's see where A condenses. So A is condensing. So A is diffusing in the stagnant film of non-condensable B on the reaching to the cold surface at y equals to 0, where A condenses, right? The film thickness is 2 mm. At the boundary of the stagnant gas film, concentration of A is 6.8 % and solution density is 988.1 kg per meter cube. Okay. At the cold surface, the concentration of A is given. So, okay, at the boundary of the stagnant gas film, concentration is given, and on the cold surface of it is given. Okay, the diffusivity of the system is given. So let me just fix it. This will be our okay. What is the steady state flux of component A in kg mole per meter square second? Molecular weight of A and B are given. Okay. So let us fix entire question first because okay. So this now this thing. So let's see how much questions we are able to solve. These are recorded, right? So there is no problem. You can go through these lecture as per your time and this. Okay. So consider a case of hot vapor A diffusing at a steady state through a stagnant film of non-condensable gas B on the cold surface at y equals to 0 where A condenses. The film thickness is 2 mm. At the boundary of the stagnant gas film, concentration of A is 6.8 weight% and solution density is 988.1 kg per meter cube. At the cold surface, the concentration of A is 16.8 weight% and solution density is 972. You see it is reduced. Why? Because at the cold surface, whenever A is going, there you see the concentration of A is getting increased. So overall the solution density is reduced. You see why. So this is very interesting to note here. The diffusivity of the solution is 7.4 into 10 minus 10 meters square per second. What is the steady state flux of the component A in kg per mole per meter square second? Molecular weight of A and B are 46 and 18 kg per kg mole respectively, right? So let's see first. If you want me to take the concept of this particular problem, uh, so this was this very well explained in this one of the lecture of the week. Let me just take the diagram. Okay, so these diagrams will help. Okay, so this just see it was I think the lecture number 33. I think. Okay, so here the heat and mass transfer were coming up in the picture, right? This is the diagram. Let me just take the diagram because then overall discussion becomes easy. So the main diagram of the problem. Okay, so let's leave this diagram here. What is this? No, it is recorded anyway, so you visit it. So this is the diagram of the problem. Cold surface is there, and according to this, you see everything is given over here. So temperature is changing, concentration profile is changing, right? And this was the part of lecture 33, which is simultaneous heat and mass transfer, right? So let me just start the solution of the same because we are having very less time and still we are going to solve 3 to 4 question or 5 question. So let's see this. Okay, so here if you see that if you want to calculate x and naught, okay, so it is given everything 16 point base 16.6%. So based on that, if you calculate x and naught, so x and naught is what? X and naught you are going to calculate, right? X and naught is equals to 16.8 divided by 56. Right. 16.8 divided by 56 plus 53.2 divided by 18 equals to 0.365 divided by 0.365 plus 4.62. It will give you 0.073. Similarly, x and delta you want to calculate what? 6.8 divided by 56 whole divided by 6.8 divided by 56 plus 93.2 divided by 18. Right? So let's see here. So when you solve it, 0.148 divided by 0.148 plus 5.178. So this will give you 0.028. Right. So at x equals to 0, molecular weight 100 kg for 0.365 plus 4.62. So it will give you 20.05 kg per kg. Okay, so what is this? At x equals to 0, you calculated this. Okay, and at x. So let me just see this. At at x equals to delta, okay, is to 100. You understand this? 0.148. Okay, plus 5.17. Okay, which is total. As by total by 9.8. So it is calculated by this is total. This is total, and this is mass. So it is saying it's a you took so what is the ratio? Okay, so now if you see almost question is solved, just few main steps are given. Those are here you are given with this density. So C is what? Rho naught by m0 plus rho delta by m delta divided by equals to 972.8 divided by 28.05 plus 988.1 divided by 18.7. So since with this molecule, and this was the at delta you had this 988, right? Let me just see 988. Okay, and at other location this is 0. This is this 970. So divided by 2. RE average concentration at 2 location. You will get C equals to 48.518 plus 52.614 divided by 2 will give you 50.57 kg mole per meter. So this will give you an average. So C will be by delta ln 1 minus XA delta divided by 1 minus XA0. Okay. So when you see this, let me just see if things are okay. Yes. So if you see this, then what you are going to get is, let's take this to the next slide. Okay, because okay, so it will be easy for you to connect these are different places very well arranged. Okay, so it will give you what? 50.57 into 7.4 into 10 power minus 10 divided by 2 into 10 power minus 3 ln 1 minus 0.028 divided by 1 minus 0.073. Okay, so this will give you minus of 1.87. No, not minus of. This will give you 1.8711 into 10 to the minus 5 ln. So I thought of putting it another way. This, if it is upside down, then there will be minus. Okay, so this once you solve, you will get 8.772 into 10 to the power minus 7 kg per kg mole per square second. So 8.77 into 10 to the minus 7, right? So it is D is correct. Let's save it. So far if you see, okay, we have solved like around 5 questions related to, I think, first 3 lectures. Okay, so far things are going well, right? Just these questions are a bit lengthy, calculative, so you have to be very cautious while writing the units and the terms. Okay, so this is that question. Okay, so if you see this one, okay, this is this lecture 33, simultaneous heat and mass transfer. In that we had the simultaneous heat and mass transfer, where the hot is diffusing in the steady state permeable transformation B on the cold surface, right? Ideal gas behavior is assumed physical property to be constant, evaluated at mean temperature and the computer neglect radiation. And here you had these things. So while solving, you have encountered different things, but the main thing is the expressions that you have derived. So this was for the composition XA, and then once XA, you want to calculate dXA by dZ to calculate the flux. And once you do that, this is see, this is the formula that we have used right now, right? And you see how well things were discussed. Each and every steps are there, but these are tedious and lengthy. I understand, but the concepts remain same. So that concepts are the one that you have to be very thorough way, right? So let me just show you another question, which is the question number 6. Okay, it is again around similar concept, very similar. Uh, okay, very similar question. So I will not spend much time on this. Whether I will have just like this. So what I'm saying is this one, this question. You see, consider a case of hot vapor A diffusing at a steady state through a stagnant film of non-condensable gas B on a cold surface at y equals to 0, where A condenses. The film thickness is 2 mm. The temperature at stagnant gas film boundary and at the cold surface is 70 degrees Celsius and 20 degrees Celsius respectively. This was not the part of the previous question, right? The temperature you are not bothering about. Okay. The rate of the mass is unaffected by the heat transfer, but the heat transfer is affected by the rate of mass transfer, right? If the very important line, this is very important line. If the molar flux of A is this, okay, what is the ratio between the rate of heat transfer in the presence of mass transfer and in the absence of mass transfer for the stagnant gas phase? These are Cp, K, and given useful equation for the also, right? So let's see this question. Okay, so in this one, if you see a very good question, okay, here and average is to what? And average equals to what? 0.0468, right? 0.0468 kg mole per meter square, right? Delta equals to what? 2 into 10 power minus 3 meters. Cp is what? 250 joule per kg per meter. K is what? Another 0.173 watt per meter. Okay, now the main things comes up. So now Na, no, N average Cpa divided by K delta. It is equal to what? 0.0468 into 250 into 0.002 divided by 0.173. This would give you at 0.1353, right? And now let me just see. Yes. Now if you see the given ratio is given here, the formula. Let's take the formula. This is the ratio that is given. Okay, this if you use it is minus 0.1353. This factor we have already calculated and divided by 1 minus exponent of 0.1 be what? 0.9. And this is the, the main thing which is asked here. Ratio, rate of heat transfer, rate of heat transfer in presence of mass transfer divided by rate of heat transfer in the presence of mass transfer and in the absence of mass heat transfer in absence of that begins right. So which answer is correct? 0.934. C is correct. So now you understand that how these questions you have to solve, right? So we will be solving if solving few more questions, but what I'm saying is uh, we will see how much time it takes, right, to actually solve each and every problems, because some problems are taking much time, right? So we will solve anyway all the 10 problems that we are having, right? So let me first add this from where this expression came up into the discussion, right? Here, if you see this one here, this direction of the movement of condensable vapor A through other condensing component B, and if you see this, uh, the main there is that the expressions the ratio of this transfer of heat in the presence and in the absence of mass transfer. Okay, that was something very interesting to know, and that is finite, right? So if you actually look at this, you will come to know about the same. So this thing we have already discussed. And this is the last part we have already discussed. Let me just see this one. Yes. So let's solve another question. Let me just take it ourselves. Yes, sixth is the seventh. So in the seventh, if you see, the question is okay. So for this thing, I am just fixing it. Okay. Now let's see. See it. It is well. Okay. So consider a instantaneous and irreversible catalytic reaction. Uh, 2A, I think 2A gives B, right? Gives B, and the product diffuses back to main gas stream immediately after the reaction at the catalyst surface. Assume that each catalyst particle is surrounded by a stagnant gas film through which A has to diffuse to reach the catalyst surface, and thickness of this film is 2 mm. Right? Designate main stream as at z equals to 0, and at catalyst surface should be taken as z equals to delta for mathematical simplicity. Flat slab-like particle surface should be considered rather than spherical for catalysis. Okay. If the main stream mole fraction of A is 0.8 at steady state, what is the flux of A if you provided the this diffusivity is this one. If you see, we just write it. This minus should go there. This is minus 8. Okay. And system average concentration is 50 kg per 8 mole per liter. Useful equation is given by this. Right. Now you have to calculate the flux. Okay. So let's solve this question. Again, very simple expression is given over here, but these expressions, how they are derived, that is the main thing that you have to actually look at, right? So if you see, as per the problem, this is an AZ is to what? CDAB divided by delta, and this is LF 1 divided by 1 minus half XZ, right? So when you solve this 2 into 50 into 5.1 into 10 power minus 3 divided by 2 into 10 power minus 3 ln of 1 divided by 10.4, so it will give you 1.203 kg mole per meter square. You see how less time this would this is correct. Only C you took 50, 2 is there, DAB you used, and delta you had the idea about, you know, and 1 upon 1 minus 1 by 2, XA naught is given here. XA naught is given here, so it's 0, 0 okay. So what 1 minus 1 by 2 XA naught, right? So this comes out to be 10, right? Okay. Now some problem. You just fix it. So this is what function of A in is 0.8 will be 2 because of the 2 gives 3 types. 0.4 6. Okay. So let's so once you see this, the B is correct answer. Okay. So where is this? Yeah. So you see, all the questions were just having some basics formulas. And if you are thorough with this explanations, whatever has been taught to you in the class, then everything becomes easy, right? And so just moving to the next problem, just rectify it. Some basics. Reaction ought to be 0.4, right? Yes. Consider diffusion combined with catalytic reaction to gives B, right? With each catalyst surface being surrounded by stagnant gas ring of thickness integrated level, and if the divisibility and the rate constant are this. Okay, then the certain what type of reaction is it? Instantaneous, not instantaneous, but not very slow there as well. Okay, so how you are going to get this? So the when we were discussing about this instantaneous, non-instantaneous kind of conversion of A to B, in that case we had a number which is called Dan-Polar number, right? So Dan-Polar number. This is what? DAB divided by K1, right? This way, this, this diffusivity and it constant is given. Okay. Then you use this viscosity. Okay. Viscosity and rate constant. Meter square per second is at the top, and here it is meter per second. So it will give out 4.5293 into 10 to the power minus. So what is it? It is close to zero. So it means what? Since Dan polar number is tends to zero, it is instantaneous. It is diffusion to reaction. So almost it is zero. So it is instantaneous, right? Okay, so A is correct. So moving to the next question, which says this one. Consider okay. Consider a system where diffusion is combined with the homogeneous reaction. This 2A gives B, where A is a gas and B is a liquid. The length of the system in which A diffuses and reacts is L. If the diffusivity and the rate constant of reactions are DAB, let's fix it. So rate functional reactions are DAB. Okay, and this K1 triple S. So let's make it K1. Then relative contribution of reaction rate constant and diffusivity can be certain by Thiele modulus and is defined as. So you know that Thiele modulus, very standard definition of Thiele modulus. It was also dictated to you in the class, right? So so let me just open that Thiele modulus lecture or the slide. Let me just take that slide to the place where these discussions are happening, right? So this dilemma is very standard equation. This dilemma plus this is that equation, and that came from the. Let me just okay. So let's keep it in on the next slide. A1 triple S L square divided by D, right? And then the K1 triple S L square divided by D. So it is B option. It is B option. So the modulus. This L square. And this is under this. Okay, so B is correct. It is a very basic thing which comes in the chemical reaction engineering second also in the chemical engineering course of the master, and this is very unique when this catalyst is coming up, right? So moving to the this, so we can discuss about the same, but the thing is very similar approach as we had already saw, right? So you see, this was the expression that comes up, and then the constants when you collect, this phi comes out to be like this, which is this similar of constant, and then that comes up. Okay, now let's solve the next question, which is a unique one related to this Taylor modulus. So let's fix it. Some typos. Okay. So consider a system where diffusion is combined with the homogeneous reaction. 2A gives. I will be just fixing it. So 2A. Let me just save it. Okay. Okay. So it is done. Let me just fix it. Yes. Consider a system. Consider a system where diffusion is combined with the homogeneous reaction to gives. So in that you saw, na, there could be heterogeneous reaction happening and there could be homogeneous reaction happening. Okay, so if heterogeneous reaction happening, then then you are having a boundary condition, right? So where a concentration can be assumed, which is the surface of the catalyst, there only the reaction is happening. But in case of this homogeneous reaction, okay, so there will be this two-way gives B. Because of that, you have to add the source term in the conservation equation, right? So where A is gas and B is liquid, okay, so the length of the system in which A diffuses and reacts is 10 mm. Okay, A is diffusing, reacting, B is 10 mm. If the diffusivity and the rate constant of reaction are 5.1 and 10 minus 8, and this 5.63 into 10 minus 3 respectively, and saturation diffusivity is this and saturation solubility of A is uh, A into B is this 1.426 into 10 minus 3, right? Okay, now what is the flux of A at gas liquid interface, right? So let's solve this question. You are given with the equation, right? So now just first calculate this term, this one, which is this under root of this is the same that we have just di- di- discussed in the last question. Okay. It will come out to be what, 5.6 minus this given this one, and then 10 into 24 minus 3 whole square divided by 5.1 into 21 minus 8. Okay, this is 10 hours. This is also 10. This will give you 3.3. Okay, now this Na, that Na z at z equals to 0 is what? Given by this C naught. C naught is what? C naught is what? 1.426 divided 1.426 minus 3 into T is what? 5 divided by 5 10 into 10 power minus 3. This one, this one, this one. Multiplied by this value, 3 point, multiplied by tan hyperbolic, 3 point. Once you solve this, you will get 2.409 into 10 to the power minus 8. Right. So this is very important. You see, so it is. Just save it. Okay. It is still saving. So okay. So the thing is, if you see, let's just export the PDF. Okay. Yes, it is week 9, right? It is week 10. So let's week 10. So just, okay. So it will take some time. Okay. So till then, let's discuss this one. So if you see this here, the simultaneous heat and mass transfer we have discussed with this particular problem where this condensable E was diffusing through this stable film or non-condensable gas B, and in that we have seen that how well this interconnection between heat and mass transfer came into the picture, and we use this energy quotient dividing the 4. Okay, to establish the entire correlations over there. So you see that all the lectures are connected. So wherever you have missed, you have to go and revisit this, because unless that you see that this was the case about this the question that we have solved. I think this particular question, right? Uh, which one? I think seventh or sixth question. Yeah, this sixth question. Sixth question are the same question. So sixth question is this MA average period. This one we have solved. Right? Okay, this is done. So we are discussing what? Hmm. Okay, so this we have solved. Okay. And in this slide, uh, part B was when both component condensing at the bottom. Okay, in that case, the mass balance you started with the mass balance. Okay, similar for the B also. To B naught, and in that case, this particular expresses shortened and calculated with tedious calculations and all, but at the end you have this particular concentration axis, and then when you solve axis, then you have this uh, in terms of flux of any flux, right? So at this because of this at delta x, this is because of thermal delta T for different thicknesses. So in order to account for variation of film thickness for both mass transfer and heat transfer, we get similar solution with changes. So for different thicknesses, when we account for different things, and also these two equations were similar. Okay, so solutions were similar. So if you solve the one equation, then other you can easily solve because they were similar. So in this equation, if you see, and this equation just T is replaced by X, right? Very similar equations. Okay, so similarly, you solve different equations. Entire week was very good. Okay, thank you. So thank you so much. I hope this lecture helped you, and we will meet again. Something new in the next week, right? So if you see this one, uh, this was the week 10. Yeah, one thing I wanted to tell you is that very less. Where is that? So very less lectures you may have seen that now when this heat transfer is one and mass transfer came simultaneously, very less non-Newtonian part is coming up in the picture, right? Because inclusion of heat and mass transfer together makes entire calculation and analysis tougher. So uh, it is helpful when you are using any tool to solve the problem, then consider everything together. But the thing remains same. Almost 70 to 60 to 70% of the course is having this non-Newtonian part intact, but only these part where we are having these simultaneous things together, then it becomes a bit difficult to include everything together. But the thing is, you see what kind of expressions or the mathematical systems we are dealing with. In those systems, simultaneously, if the fluid is non-Newtonian, then another type of complexity will be coming up into picture, and inclusion and consideration of that will be anyway having very good formulation of the problem, which is very close to the real system, right? So it is kept for you to explore much in this, and then use different numerical techniques wherever or whatever you are doing. Maybe it will be helping you in your research for. So that's why this course is prepared. It is a advanced level fluid dynamic course. Again, this transport phenomena course. I can't say fluid dynamic course, and then it requires some basics of basic transport phenomena and masters will come from that's right. So thank you so much for your kind attention. And I think all the videos are getting recorded. You can revisit these videos as per your will. So this is having a compact question answer session of whatever things you have been taught in the entire week. And through the questions, we were going to the concepts that have been taught by sir, and we were discussing about them, uh, doing the calculations, whatever playing with the units and everything, and feeling the problem. So the main integrity of the problem, or main crunch of the problem, why this problem is given to you, and how this problem is important in real time system, right?